So this live cast is about memory space usage. Maybe even put that in. Memory space usage in Python. And I might zoom in a tiny bit. If I've got space to zoom in one more, I'll do that. And I'll switch off all of my volume as well. And I've imported this module here, which will be used later, because the one piece that I'm going to actually take out of this module is the get size of method. So we'll go through that. But in the meantime, I've also imported this module, which is import numpy as MP. And basically, I guess the first thing to do is we'll look at this as sort of like a little game here. But if we can guess which ones of these, if we could put them in an order in terms of the memory space that they occupy. And over here, we've got this is a set, and then this one here is a list. But this list is a list, but it contains one number. So it contains one number, right? And the set contains one number as well. And then you've got over here, we've got a string. This is to help us out. And here we've got an int, so an integer. And this one here in Python, if we've got even though this 10 is the same as this 10's got a 0.0 at the end of it, and that makes the difference. So, or at least if I get my little pen out, this little 0.0 piece here tells Python that this is not going to be an integer anymore, but it's going to be something else. It's going to be a float. So that'll be a float. And finally here we've got an integer, but we've got like a numpy integer of bit size 16. So numpy, like some form of restricted size, some sort of form of restricted memory size. And the thing is to basically guess which, or put them in order. Put the above list in order. So that's kind of like the game. And you know, maybe I'd say if you're watching this not live, that you could, if you're watching this not live, that you could actually put your own order there, and sort of like pause the video and then unpause the video 10 seconds later. So go ahead and pause your video, and then and now go and unpause your video, and we'll have your guesses in between. If you haven't had your guesses, have your guesses, pause the video and then unpause your video. And then but in any event, it's kind of like, yeah, let's see how good the guesses are, and we're going to sort of like guess in the order of, like, you know, U, V to W and so forth. So we're going to put them in some kind of order. The smallest, should we say, put them in order, smallest to largest memory, right? And I think that should be good. I'm just going to do a control minus because that's our 70 line limit or 80 line limit respect for Python code. So, you know, I don't know what one might deem to be like a reasonable guess. I know the answer, but I know what I might have guessed, at least in the beginning, which was I'd probably put, you know, and you could argue with me on the screen. I wonder actually if I can get my if I could put up the YouTube channel somewhere. I wonder if I can do that. I have got a YouTube thing, so maybe I'll get that to the side. Yeah, I'll open up a new tab somewhere and I'll do that. So YouTube live, I could click on it, bear with me. I'm just wondering if anyone's actually on live stream, or if I can view the actual live stream. Right, so just returning, and actually it's actually the use of, no, that's not it. I was trying to go to the live stream. Back. Right, live. No, I can't see it, but by all means put your comments in the comment section, and we'll see, we'll see how those get along anyway, in any event. So but I'll go through what we might have thought would have been the smallest to largest. So probably something like integer, the integer, so that will be x. I might even like list them. And I guess part of this is maybe that is, well, is it going to be intuitive as we think it is, or is it going to be unintuitive? Then we might go something like, I'm going to guess, well, we might have even guessed that, go here, that z would be the first one, because it's some sort of numpy thing. Why might that be the guess? Because this is efficient and sort of like smaller, so an integer might take up a certain number of characters, and then the numpy one, well, that's restricted to a size of 16. If this was like, its standard size was like 30 or something, and this int 16 would use a fewer number of bits basically. So we might have guessed a numpy integer. Then x would be the next one, which is just our standard integer. Then probably somewhere in between, I don't know, maybe like we could think that lists, a list is going to have to set up a bit of space to have the list, and then inside of that list, it's got the integers. It'd be a bit bigger than an integer, but I'm not sure like which ones would come next between the u, the v. Maybe a set is like slightly more efficient than a list, but I don't necessarily know if that's the case or not. And then does a float come next? So maybe we might think that these two, so these are sort of like containers. They're containers, which is a list and a set. And then somewhere again competing or arguing, but possibly like we'd go with y next, which is a float, and finally we might go with w, which is a string, because a string, I think it has to set up the most space, but then the string is only a small size string because it's only 2 characters, so it's a 2-character string. So right, so maybe it isn't a big string, maybe it is big, maybe it isn't. So that's kind of like the question, and that might be initial guesses. I know what the answers are, so it's a bit unfair for me to say, but I would have like ranked kind of like, at least I'd put the integer probably at the top, or the numpy integer. Let's spell it integer right. Let's just pull that up again. Yeah, that's fine, okay. So yeah, what are we going to go for? But I guess one of the things to say on that is we can use this get size of things. So we'll just pull out the answers and see what happens. So there's a function called, so in the sys module there is a function called get. There's lots of get things. Get size, we can see it down here. Get size of, so tab, open brackets, and then whatever object that we want to put in there. So for example, like u, so get size of u, and wonder if when I did the open brackets, if it actually gave the little comment. No, I didn't. But if I hover over it, will it give us any commentary? No. But I guess I could pull up right in Python get size. Python get size of. Right, so there we go. More length and get size off. So let's actually pull up the actual docs. So we've got the docs over here. Zoom in a little bit. Plus. So it's in the sys module. So let's just look at for get size of. There we go. So this is the actual function that we're talking about, and it here, like to get the full definition. So I can close this down now. Return the size of an object in bytes. This is how many bytes the object is. I'll zoom in a bit more just so it's clearer. I've just lost it. There we go. Zooming in. If I zoom in again, I'll probably lose it again. Yeah. I'll just get size. There we go. Right. So returns the size of an object in bytes. The object can be any type of object. So an int, a float, a string, a list, whatever. All built-in objects will return correct results, but this does not have to hold true for third-party extensions as it is implementation specific. Well, I'm not 1,000,000% sure what that means, but okay. Only memory consumption directly attributed to the object is accounted for, not the memory consumption of the object it refers to. Okay, fine. So yeah, and I think that's pretty much it. If given, default will return. Default will be returned if the object does not provide means to retrieve size. Okay, fine. Type error will be raised. Okay, fine. But anyway, we get the idea of it. It's just going to get the size of the object. So we're going to basically be using that function over here, and we are going to allocate it. We're going to put it into a print statement. I had a pre-print statement written out, which is basically this. So for example, if we wanted to get the size of this variable here, u, so you know how much memory space is this actually occupying. So I can sort of like just run this piece of code with a control return, because I'm not going to run it in a Jupyter and an IPython notebook here. So an interactive notebook is probably the best phrase. And we see that u is 216, so that's 216 bytes, and we can do the same for v. We stick in v, and we see that v is 64 bytes. So this container here, this set, is occupying a lot more memory, funnily enough, than this list, which is an interesting one. May or may not have thought that. And we keep going down the list, and I guess you can like guess yourself before I do each one of them. So again, you sort of like pause and open or whatever before each one. But I'll put in W. I can't see the comments if there are comments on there, but W, and W, which is the string, occupies even less space. And at this point, like, I'm kind of like going to say I'm already baffled here, because I've put on my list here that the string would occupy the most space, and there's explanations for it. Like there's some setup cost is actually what the explanation is for these things. There's some sort of overhead to having a list and having a set, because you have to sort of like define it first or something. So some characters are possibly, or some bytes are possibly used for that. But then we continue to plod along, and we'll go next. We are on to x, which is the integer, right? And we're expecting x to be the lowest. So we run that, and down below, and look at that, lo and behold, x is like, you know, right up there. You know, maybe the only thing that's lower than that is going to be this numpy integer. And I might have already given a bit of a hint away, but maybe this numpy integer won't be, because if there's some sort of overhead. So, you know, we've still got a few letters before we get to there. We've got the y and the z, y to get there first. But we're expecting y to be larger than x just because there's a little extra bit here. There we go. So we put in a y, and we put in a y over here, and our results are just going to come down the bottom, like just, you know, in this little section. We're just going to update that for the y. So I'm going to rerun that, and lo and behold, we do not get y being larger. So the integer, sorry, the float is actually smaller in size. It occupies less bytes than the integer. So that is the one that really actually throws you completely. Well, I don't know, throws me through me, because I had to go and look it up as to why. I was expecting integer to be the most cost-free, at least in Python, in the Python framework that we know of. But finally, anyway, now the cat has been thrown amongst the pigeons. You know, Z, you know, we want that to be the most efficient, because the whole purpose of Z, like especially in terms of, like, you know, I've had to type out this extra piece here, numpy.int, and numpy is this really memory efficient piece of mechanics, you know, that's written in C++, and we're expecting that to be the most memory efficient of all. And the reason why I was doing that is because I was like, well, maybe I can iterate through a list faster if the list was not a numpy list, like a numpy array, but if the numpy, if it was just an integer and I was sort of like counting, maybe if the integers were smaller memory bits, I might be able to traverse through them a little bit quicker. But anyway, it turns out that, you know, we'll see. But when we run this again, so hit control return, that even the numpy thing is actually bigger than the bigger than the float. So that's kind of like the order of it all. And yeah, so then I'm going to say is numpy, just so it's all labelled. So that's numpy. This was the float. This was x was the integer. W was the string. I'll put colours off them. And then we had the list over here. And finally we have the set over there. So just for clarity, you know, it looks like that. And I just sort of like, I guess I'll delete that bit here. So it's all of this stuff down at the bottom corner. So our numpy 16-bit integer is actually, is that right? Well, the numpy 16-bit integer is smaller than the integer. So I was hoping for that, so that's good. That kind of like gets a tick. We like that. So that one gets a tick. But funnily enough, it doesn't beat the float, and this is the winner here. This is like the winner. Right? And, you know, I don't know what we're expecting here, but that's actually the integer. And that, you know, we might have, it was going to be between, like, in my mind at least, it was going to be between these two, the integer and the numpy thing, and it, you know, wasn't definitely wasn't going to be the float, because the float literally contains a little extra bit, and all my knowledge of coding and everything else, you know, you have to just assign more memory space for floats because they're just potentially a little bit larger. So I go on to ChatGPT somewhere to ask the question, because, you know, that's kind of like the point that we're at. I wonder if I had it. I didn't ask it over there. No. Right, so I'm going to do a zoom in. I'll start a new chat here, and assuming it works. Python new chat. There we go. And zoom in a little bit. Get rid of this sidebar if I can. Yeah, I can get rid of the sidebar. And what were we going to ask in the chat? And in fact, let's ask ChatGPT the whole thing. Which of the below uses, so I'll put that into this actual screen so we can see, which of the below uses the smallest amount of memory? And I'll paste them all in there. Put in order of smallest to largest. Right, let's see what comes out and what's going to come. Here's the analysis of memory usage for each variable. So x is an integer, right? So it's guess this one. Python integers are objects. Their memory usage depends on the size of the integer. So I've used the 10. However, even a small integer like 10 uses 28 bytes on most systems. So there we go. All right. And there we go. So it does know that floats are 24 bytes. I wouldn't have guessed that. I just, so I will ask the question later, I guess, which is why does a float use more bytes, use fewer bytes of memory than an int? Because that's going to be a question. But anyway, next we've got here x, y, z. Has it already put it in order? No, it hasn't put it in order. Okay, fine. Z is the NumPy integer. A NumPy 16 uses a fixed 2 bytes, 16 bits for the value itself. So that's the piece. Plus a small overhead, and that's the cost being part of the NumPy object. However, the total memory is typically much smaller than the native Python integer. Well, yes, it is smaller, so that's fine. So it got that, but not a float. So it's still sort of like on course. W, okay, which is 10, which is a string. A string 10 typically uses 49 bytes. And if we just go back there, it wasn't too bad as a guess. The string here was 43 bytes. So not too bad, I guess I get, I suppose, on most systems. So it's sort of like being generic here. I don't know. I haven't got any great system. I'm just using a regular standard PC. So the list is saying it's 64 bytes. A Python list has its own overhead. So we have that plus space for the reference to the integer object it contains. Okay, so you've got some overhead, then you've got a reference. A single element like 10 is typically 64, and it got the list completely right. And then finally the set. So I wouldn't have guessed this at all, but now we're being told, like explicitly, a set has a larger overhead compared to a list because it needs additional memory to handle hashing. Well, there we go. Okay, a single element set like 10 typically uses 232 bytes, and it wasn't completely accurate. It's 216, but it was pretty good. So it's got it as a guess. So order from smallest to largest. Let's have a look. Should we even take them off? Oops. So Z came in as the smallest. Oh, funnily enough, yeah, it thought that Z would be the smallest because it thought it would be, well, it's saying it's 2 bytes, but it's not. Okay, so Z is not the smallest. It's 2 bytes on top of, I guess, at least the 24 for the float. Float's next, integer's next. So it did get that. Then it's got the string, the list, and then the set. So we're not really surprised too much about too many of them. Maybe a tiny bit on the NumPy thing. We might need a bit of delving explanation. But the real question is why is the integer larger than the float? Or at least why does the integer use more memory than the float? Question mark. So let's see what gets fired back. Don't want it to. I should have put in 4 lines. Oh yeah. Answer in 1 paragraph. Right, otherwise it will speed on and on and on for a long time. Let's hit the return. Let's see if I can answer such a question. Right, okay. In Python, int is an arbitrary position object. I did actually read this earlier on a different version thing, but it's an arbitrary position object, meaning they are designed to handle very large numbers beyond the limits of the fixed data types. Okay, this flexibility comes at a cost. Python integers have a higher overhead because they store additional metadata such as size and sign information. Well, both the float has sign information, but yeah, you could argue if you're like restricting the size of a float that the int being dynamic might cost you more. In contrast, floats in Python are implemented as double precision 64-bit numbers, which are more compact since their memory layout is standardized and doesn't need extra metadata. So it's this extra metadata for to be able to allocate this variable space. But I just still thought that there would have been a gain. So maybe, you know, the difference might be between 1 and 1. I don't know if we change that to a 1 and this to a 1.0. I wonder if there's a gain there. So like we'll compare the int to the float. No, it's still the same. I don't know if at some point, like without, you know, I could muck around with them and sort of like do a comparison. I guess that's pretty much it. As a result, float typically uses less memory than integers for small numbers. Okay, so let's put in a big number. So an integer, we'll go to 123 underscore 123. So that's 10 million. 10 underscore 123 underscore 123. So that's 10 million of each of them. And there's no change there. I'm just going to keep on adding zeros. I just don't see, so we're comparing the integer to the float, which is x and y over here. Just keep rerunning it, just see. Doesn't seem to be changing, so I'm not necessarily even sure if at all ever. It just looks like integers, just use bigger numbers. In fact, this one's grown in size even more, whereas the float hasn't grown in size. So there we go. Maybe I should be counting in floats from now on. I don't think you can count in floats. But yeah, so I might put this in. As a result, floats typically use less memory than integers. Would this be any different? Right, and we know that it wouldn't be different because we've just seen it. Right, hit send. Because Python integers are arbitrary, so forth. This is saying that this is the exact size depends on the platform, but will be larger than the standard 28. So that's correct. Python float remains at 24, so it's not really. It says So the last bit of this, and this is why I guess you can't fully listen to GPTs, but the last bit of this is not correct here. Implemented as this piece here, as a result, floats are typically less memory than integers for small numbers, is not actually true. Or sorry, it is true, but it's actually true also for big numbers. It seems to be true for every number. So a Python float remains fixed. There we go. So this is always going to be 24 bytes, regardless of the magnitude of the number, as it uses this double precision format. Okay, fine. So yeah, so that will never change. So I guess when using, well, we like to use integers for other reasons over float, because you get floating point arithmetic problem. You know, and then that was another video somewhere where I sort of like do, I think 1.0 plus 2.0, and you get this funny answer. But anyway, let's read the final piece. The memory usage of the float y remains constant at 24 bytes, while the integer will require significantly more memory to store the larger number. As the size of the integer grows, its memory usage increases, unlike the float. Therefore, for very large numbers, floats can be more memory inefficient than integers. So, you know, we go back and we can remove all of these zeros, because if anything, that made it worse, and we were told that it made it worse. In fact, we'll remove more zeros. We go back to the 10 and the 10.0. But there's some oddities that you do get, which is, I think, I don't know, like if it's, so I'll put y1 equals 1.0, y2 equals 2.0, print y1 plus y2. I just wonder what's going to come out of that. And like, fine, it did stick in the 3.0. There were some odd things where, like, you get 2.999 something with a floating point error at some point, but it's not caused by that. But it would be caused, it's caused by something else that's quite similar and innocuous. So you can't just replace integers with floats. And I think, well, you certainly couldn't in sort of like a for loop or whatever. So you couldn't do like for I in range. So something like this, 10. You couldn't put in for I in range, so print I. So you might want to do for I in range 10, print I. Delete and run that, and then you get all of your numbers, not 10. But if you were to bang in a point in here, I wonder what would happen. Yeah. So unfortunately you can't do that, because you get this error message over here, which is the float object cannot be interpreted as an integer. So we can't just switch to the smallest memory size piece if we wanted to. It wouldn't be a great example in the range thing anyway, because it's iterable and it's iterating over something. So it doesn't make sense. And it wouldn't really be that much of a cost saving, because at any point in time we'd be using 24 bytes versus 28 bytes or whatever it was. And it wouldn't be an additive gain. You wouldn't be gaining 4 and gaining 4 and gaining 4. All you'd be doing is always just using 28 versus 24. You just gain 4 the one time, so it'd be no big gain. But I think that's kind of like, the end of anything that I might think is relatively interesting there. I guess the most interesting takeout was this float piece, but we were told why the float was the most efficient one. In particular, I guess this sentence here, which is it just remains a fixed 24 bytes regardless of the magnitude of the number. But we can't do like all types of floating point stuff. I wonder if this was, I wonder if I can do a Control Z a few times. Get that back. No, I don't even think it'd be the case with the times. And it was really odd because when I did do it, it wasn't for all numbers. It was for some numbers it worked out to be the case. No, because that still gives you the 2.0. I did have it in another video, but yeah, you can go and browse through the videos. Anyway, if you found the question, the initial question, which is, I'll get rid of all of this stuff. If you found the question interesting at least, or informative, which was, put these in order. We've learned something about what happens to Python under the hood, and we used this little function that exists in the sys module. So this function, which is a get size of function, that lives in the sys module to get the byte size, the size of the object in bytes of any given object, basically. And we established that floats were the most efficient. The NumPy integer was quite good. I wonder if the NumPy integer, well, I guess the NumPy integer would have a saving. So I guess that's one thing to investigate before we just close up. Which is NumPy is 26 bytes here and an integer is 28. I just put in loads of zeros, so something like that. Maybe I've been putting another 3. I don't know, just to use up lots of things there. Bang that one in. So now we're going to be comparing the int here, which is 28, to the NumPy, which is 26. We know that the integer grows, so the question is does the NumPy one grow? Or does the NumPy one actually throw an error because can it express this value in 16 bits? I'm not sure. I don't know if it can. No, it doesn't. Int is too large to convert to C-long. So I'll have to reduce that a little bit. Or turn it to a NumPy 32. Still doesn't do it. Right, and now it just, hold on. Right, it's giving me a comment. That's an interesting one. But the integer here is at 28 bits, so for the old behavior, usually empire.asTime, well, we'll give it, okay, fine. Yeah, so I might give up the ghost on that a little bit, or at least int 32. So now that's the NumPy here is 32 bits. Let's see the costings. Now it's 28 versus 28. Oops, 28 here versus 28 over there. And now let's start banging on the zeros. I don't know if I'm putting too many zeros again here, but we can. Run it. No, okay, fine. 1, 2, 3, lots of zeros. 1, 2, 3, lots of zeros. Control return to run it. No, still doesn't. Okay, fine. It's very restrictive, but that's what NumPy's for. Yeah. So they're kind of like the same size. So there's no like visible memory space gain at this point, at least. I guess NumPy. So like when you're using a single float and a single int32. You're not gaining on a single basis, but when these are all compiled into a contiguous block of memory, that's where you get your gain in NumPy. So you're not getting any gain from having a single. There's no gain to be had by expressing the number 10 as a NumPy int of type 32 or 16 on its own in isolation. Any gain that comes about is when you have a list versus a single variable. So something like my list equals, and then 10. This is going to be inefficient, right? because it's, you know, a type list, whereas when this list gets large, so something like maybe 10 for X in range. So you got a list of like 1,000 items long. List of all number 10s for that are 1,000 items long. And then you got my array equals, and then there is an array function in Python, but this is much more popular, so an mp.array. And then whatever, well, in fact, we could actually pass this list into the array, and I think already that the array will be, we could do the get size of it on both of them as well, so I can pass that in here, and then do, it's more of an interesting one, maybe I'll just comment all of these out, and just take these two and compare them, so uncomment them out, and then put my list, what would I do there? Oh, I had my control key. Okay, so my underscore list, and this will be my underscore array, and then we're going to get the size of my list. So my list and my, I'll get rid of that underscore, and then there we go. My listy turns back into my list, and then I will try and compare the sizes. And we see here that this list is way more inefficient in size than the array. If the list was smaller, so there's only 10 items in there, and we rerun it, we can see that the list now actually, and the array are kind of like of the same order of size. I wonder if you can get it, although we knew that any element, but there was basically, the point is that there was this quite a large saving. So now that's a bit bigger. When we run it, we can see that there's quite a huge saving, like I guess it's half the cost basically, 40 over 84 basically, so it's sort of like half the cost. I think it was linear as well in the game. Now it's taking a lot of time to think because it's got to construct this really like much longer list that's 1 billion items long, and then it's got to, I guess afterwards, get a piece of memory space. So I wonder actually if it does it or if it crashes, because it's taking a long time now to do the setup. This X for X in range. I think at this point, while it's doing its thinking, I might actually just go back onto make a numpy list array of tens. That is one. Of size. That is full of tens. There we go. Oops. Then hit return. Yeah, there we go. Okay, fine. Create a numpy array. So we use this mp.full. That's how to create the array, I think. Or you do mp.ones times that. I've never used the mp.full, so that's quite a nice one. I'm going to actually hit the interrupt. I'm interrupting the kernel. If I can, we go, okay, interrupting kernel. Okay, restart. just because, well, you get the idea that this is never going to happen. So I'm actually going to comment this one out, / and then go on to, I guess that's already seeing the gain of NumPy, which is NP. I've never used the full before, FULL, so NP.full, open brackets, and it sort of like says what it is: return an array of a given shape and type filled with value, filled with a fill value. So that's quite cool. So one, maybe this is going to occupy too much memory. I'll go to town on it there, but that's quite a large piece of thing. That my list isn't here, and then run it. Okay, well, it's come to its answer much quicker. Unable to allocate 3.6 terabytes for an array. Okay, fine, I've been like well too big. Maybe I can push my limit there. That's going to still be gigabytes. I think that's still probably be too large. No, it's done it. We can see how fast it's done it as well. So the NumPy list kind of like died its death at a certain point. Sorry, the my list in the list list comprehension here that I created. I mean, it took forever. I don't know if it was a range that was just constructing this list and going on and on, filling up memory space basically for each item in the array. So literally, was it doing something like this, which is you sort of like, well, you don't even have this predefined memory. So basically, I'll do an undo of that. It's basically you get x equals, you get your first item and it goes there, and then you get your next item and it goes and plonks it on there. That's why lists are slower. And then it goes along and does the next item, and then it goes along and does the next item, and so forth. So, and this is a very, very slow process. So it doesn't know, because it just does each one sequentially, one to the other. It doesn't know that it's going to get up to like a billion. So it doesn't know it's going to do a billion of these. So it just keeps going on. And then when it gets towards a certain point, it's going to try and find like a little piece of memory somewhere, because as you've occupied all the memory, and it probably can't find it. So maybe at some point it will crash, but it will certainly hang. So that's that piece of it. Whereas the NumPy one, it goes along and it goes, right, I need to allocate this much memory. And when it threw us the error, it was like, well, have I got this amount of memory? Because if like I only had this much memory, like from here to here, then I'm just going to throw you an error at this point, because that doesn't exist. So NumPy kind of like knows ahead of time what it's going to do, and it knows how it's going to chunk it all out, and it was able to do it very quickly. So that's just something, I guess, all about memory sizes of objects. It's a little bit further than I wanted to go, or was going to go, but it's quite a nice little delve into it. So we learned a decent amount about this. We learned that integers come with an overhead, so they aren't, because I really did think they're the most fundamental type, but floats, which have are forced into a mini structure, should we say, they're the most efficient. And then again, like I would have thought that these two things here, these containers, would have been similar-ish. If anything, actually, I might have thought that the list would have used a bit more memory than the set, because sets tend to be more efficient. But I think part of the efficiency gain comes in the cost of memory usage afterwards, as in when you look up things from a set, and the sets at the beginning of a dictionary of O of one like complexity for lookup, whereas lists you have to like traverse through the list. So when you're looking up items in a dictionary, they're much faster than lists. So that's it. If you found this helpful, do a thumbs up, a like, a follow, share it with other people, because for the sake of it. And that was a bit of a live cast. Everything I do is live. So if there's errors I make along the way, then I've got to make them. And no pre-scripting or editing. That's pretty much it. So I'm going to sign off.